going to look at the proofs of various things here, complicated looking things. First thing we're going to prove is that this is actually the solution to the discrete time Lyapunov equation. So how does that work? So again, if the spectral radius is strictly less than 1, then a to the power t goes to 0 as t goes to infinity, and so this infinite summation is well defined. So usually when we talk about an infinite summation from 0 to infinity, we usually look at partial sums. We go from 0 up to some large number and take the limit as that large number goes to infinity. So we actually work with it in terms of limits. And so we actually work within the limit of a sequence, and so those are the kinds of things we look at. So this summation is well defined. So now if I look at this quantity minus this quantity, so I can actually write both of these as linear, as these kind of summations, and put them under the same summation sign. So here I have a transpose a to the power t transpose, so this combined gives a to the power t plus 1 transposed. And similarly on this side, a to the t plus 1 minus a to the power t transpose q a to the power t. Now, if I look, for example, at t equals 0, this is going to give me a transpose q a minus q. If I look now at t is equal to 1, I'm going to get a squared transpose q a squared minus a transpose q a. So notice I have a minus a transpose q a when t is equal to 1 that subtracts from a transpose q a when t is equal to 0. We have this what's called the telescoping difference. And so what happens is that every term in this infinite summation cancels with some other term in the infinite summation, except for the term at t equals 0 and the term as t goes to infinity. Because of the fact that t goes a to the power t goes to 0 as t goes to the infinity, then that term, so when I'm evaluating this at time t equals 0 and t equals infinity. At t equals 0, we're going to get 0. T goes to infinity, I'm going to get 0 because of this. When t goes to 0, I get the identity, which just gives q, minus q. So a transpose p a minus p is equal to minus q, and we have a solution to the discrete time Lyapunov equation. Now we have this relationship if the spectral radius of a is less than 1 and q is positive definite. So notice over here, I didn't require q to have any particular sign. Now I'm going to require q to be positive definite, and I want to prove that p is positive definite. So one way to prove a matrix is positive definite is to show that this quadratic form is a positive definite function. So that's what we're going to do. We're going to show that this is a positive definite function because that's one of those two are intimately related. Positive definite functions and positive definite matrices. So I'm going to prove that this is a positive definite function, which means I have to do two things. I have to prove that this quantity is greater than or equal to 0 for all x, and that it's equal to 0 only when x is equal to 0, if and only if x is equal to 0. Okay, so this quantity then, I can replace p by the infinite summation. I get this. And now I'm going to do a little tricky thing called a positive definite square root. Okay, if q is a positive definite matrix, any positive definite matrix has something called a positive definite square root. That is, q square root times itself gives q. And you can easily see how to compute a positive definite square root. If you think in terms of the singular value decomposition of q, if you take, so you have, because q is positive definite, you actually have u, s, u transpose. That is, u is the same on both sides. The s, if I take the square root of that, and I take u s to the power 1/2, so, and I take the remember when you take a square root of positive number, you have plus or minus. I'm going to take all the positives, okay? And so that gives me the positive definite square root. And so this is the positive definite square root that I'm looking at, okay? And if q is positive definite, the square root will be positive definite because the diagonal elements of the s are just going to be the square roots. Since they're all positive, the square root is also positive. The positive square root is also positive. non-zero. Okay, so I have this quantity now. So here I have this quantity, and I have its transpose. Notice that because q is positive definite, it is symmetric. So q to the power 1/2 is actually equal to q to the power 1/2 transpose. So I have this and its transpose. And so that gives us the norm, actually that should say the norm squared, times of all of this. So clearly, if I'm taking the infinite summation and each of these guys is non-negative, then this infinite summation is non-negative. Okay, so that's what we have. So that's the first part. I need to show it's non-negative for all x. For any x, I get something. This cannot ever be negative. Okay, so it's always non-negative, and I need to show now that when x is equal to when this is equal to 0, x must be equal to 0. Vice versa. So this can only be 0 if and only if each of these terms is 0 for all values of k. Okay, for all values of k greater than or equal to 0. Now, when k is equal to 0, notice what happens. When k is equal to 0, a to the k is the identity matrix. And so I have q to the power 1/2 times x. But q is positive definite, therefore it is invertible. The only way then this can be equal to 0 is if x itself is 0. So x is equal to 0 if and only if this is equal to 0 for all k, which is equal to 0 if and only if v of x is 0. So we have proven the discrete time Lyapunov equation, and we've proven that p is positive definite. Okay, sweet. Alternately, I can do it this way. Let lambda and v be any eigenvalue eigenvector pair of A. That is, AV is equal to lambda v, v is not equal to 0. I'm going to pre-multiply my Lyapunov equation by v adjoint and post-multiply by v. So in general, I may have a complex eigenvalue and associated complex eigenvector, so I need to use the adjoint complex conjugate transpose. So 0 is equal to all of this stuff, right? Because all of this stuff is 0, so v adjoint v times that is 0. I'm going to distribute v adjoint to every term and a v to every term, and this is what I get. Because AV is equal to lambda v, I can take the conjugate of this equation, and that'll show that v adjoint times A transpose is equal to lambda conjugate times v adjoint. And so this is going to give lambda times v. This is going to give lambda conjugate times v adjoint. And so altogether, this is going to give lambda times lambda conjugate, which is the magnitude squared of lambda, times v adjoint pv. So the a goes away. Here I have v adjoint pv. Here I have v adjoint qv. I can factor out the v adjoint pv from these two terms. Okay? And so I have all of this must be equal to 0. Now, since Q is a positive definite matrix, this quantity is positive. So in order for these two things to add up to 0, if this is positive, then all of this stuff must be negative. Okay? And in fact, they must be exactly equal and opposite. Now, since spectral radius of A is strictly less than 1, that means the eigenvalue of A is strictly less than whatever eigenvalue. So notice I just picked an eigenvalue, right? Any eigenvalue, eigenvector. Since the spectral radius is less than 1, that means the eigenvalue must have magnitude less than 1. Because the magnitude of whatever eigenvalue I pick has to be less than or equal to the spectral radius, which is less than 1. Okay, so lambda squared in magnitude must be less than 1, so this quantity must be negative. Okay, so this quantity is positive, this quantity is negative. So what does that say about this? Okay, what does that say about this? Well, I'm getting to this, but what it says is, what happens if this were 0? Could this be 0? And the answer is no. The answer is no. This cannot be 0 because this is positive. And so these two must be equal and opposite. So since this is positive, this cannot be 0. So this is strictly negative. This cannot be 0. Could this be negative? No, it cannot be negative. And the reason it can't be negative is because a negative times a negative gives a positive. There's no way I can get two positives that add up to 0. So the only thing that this could be is positive. Okay, and again, since V is any eigenvalue, any eigenvector, an eigenvalue, this holds for all eigenvalues and all eigenvectors. Therefore, I can go through and show that P must be positive definite. Okay, so this holds for all eigenvectors, eigenvalues. So we have that relationship, and so we have proved this is an alternate proof for this that is not based on that infinite summation that we're talking about. So this this whole process can also be used to evaluate the discrete time Lyapunov equation in the case we have unstable eigenvalues. I can still evaluate it using the same eigenvalue eigenvector approach. So altogether, we have this equation, and we have basically shown this twice. This is the Lyapunov theory, and it's fairly straightforward to go through and show this as well. So if A is a magnitude less than 1 and P is positive definite, then Q is positive definite. So we can actually go through and show that as well. All right. What about continuous time problem? In continuous time problem, if A is Hurwitz, that is, if it has all its eigenvalues in the left half plane, right? The left half plane, and Q is positive definite, then we need to have P positive definite, and P satisfies this equation. So I need to show, first of all, that P satisfies this equation, and then I need to go through and show that for positive definite Q, P will also be positive definite. This follows very similar to what we had in discrete time. Again, if A is Hurwitz, then e to the at goes to 0 as t goes to infinity. And so this integral is well defined. That is, it's integrating out to infinity, but these things in the middle are going to 0 as time goes to infinity, and so this integral is well defined. All right, so if I look at this quantity now, A transpose P minus plus PA. So here's A transpose times P. So notice I have this extra A in here, and here I have this extra A in here. So this is PA. I can put these both under the same integral sign, and I can show that, in fact, this derivative with respect to time of this quantity is going to give a term like this plus a term like that. Okay, so all of this, these two terms combined, can be shown to be equal to this. That is, I take this prime times the rest plus the rest times this prime, and I'm going to get an A coming out. And notice here I have the A on the right. Remember, e to the at and A commute, so I can easily put it on the right. All right, so this is what I have. And what do I have? I'm using the fundamental theorem of calculus to show that the integral of a derivative is the evaluation of the function at the limits. Okay, so this is the antiderivative. And so I evaluate it at the limits. At infinity, remember, e to the at is going to 0 at infinity, so I get 0. And I evaluate it at q. I'm sorry, at 0. At 0, e to the at is the identity, and so I get 0. I get q. And so A transpose P plus PA is equal to minus q, showing it solves the equation. That's the first part. Now we need to show positive definite. To show that P is positive definite, we again examine the Lyapunov function, x transpose Px. So here's x transpose Px now in the integral form. Again, I'm going to use a positive definite square root of q, and so I can show that this quantity is equal to the norm squared of this quantity as time goes to for all the integral from 0 to infinity of this quantity, it must be positive or non-negative. I cannot get a negative quantity coming out of this. This quantity is at least 0, probably positive. Okay, so for any x, there's no way this can be negative. So I've shown, so again, to show that P is positive definite, I want to show that V is a positive definite function. So here I've shown that for any x, v is non-negative. Okay. Now, I also need to show that when v is equal to 0, that x must be 0, and so forth, and vice versa. Clearly, if x is 0, then v is going to be 0, because all of this will be 0, and I'll integrate 0 for all time, which gives you 0. Okay. So what this shows then is that since this integral must be, if v is 0, that means this integral must be 0 for all time, which means this norm must be 0 for all time, which means this quantity must be 0 for all time. This is actually a vector for all time. At t equals 0, this is identity. And so what this shows is that since Q is a positive definite matrix, then the only way this can, and actually I can go through and show that e to the at is non-singular for all values of t. But clearly at time equals 0, this is not 0. And this is not, and this is positive definite. So all of this is non-singular. So the only way a non-singular matrix times x can be 0 is when x is 0. And so we have this relationship. So this shows that P is positive definite. Alternately, we have this relationship, A transpose PA. If A is Hurwitz and Q is positive definite, I want to show that P is positive. Again, I'm going to use eigenvalues and eigenvectors. So let lambda in V be a generalized eigenvalue-eigenvector pair of A. AV is equal to lambda V. V is not 0. We pre-multiply by V adjoint, post-multiply by V, and we obtain first this quantity. Okay. Distributing through the V adjoint and the V, we get this expression. Again, I have an eigenvalue relationship here that gives this. I have an eigenvalue relationship here that gives lambda times V. Here I have V adjoint PV. Here I have V adjoint PV. I can factor that out and I get this. If I take now, so I have this quantity. If I take any complex number and add its conjugate, I get 2 times the real part of that value. Okay, so this gives this. Now again, we have all of this must be add up to 0. Q is positive definite, which means since V is non-zero, this must be a strictly positive quantity, which means this must be a strictly negative quantity. Since A is Hurwitz, that means the real part of every eigenvalue is strictly negative. So this is strictly negative. And so the only way this can add up to 0 is for this to be strictly positive. Since this is true for any eigenvector, it holds for all eigenvectors. And so we can go through and show that, again, P is positive definite. Cool. Another thing that we can prove for both discrete time and continuous time is the uniqueness of the solution. So here's the uniqueness of the solution. So A transpose P, A, suppose there are 2 P's that satisfy the equation. Okay, suppose there are 2 P's that satisfy the equation. And we know that this P is given by this formula. So I'm going to use that formula. Okay. I'm not going to assume this formula holds for this P1. I'm not going to assume that. But what I can show is that P1 can be written as, again, the integral from 0 to infinity. So this is kind of like backwards way of looking at the proof of this formula. So it's the derivative, the integral of the derivative of this quantity. So differentiating this quantity, I get all of this. Okay, I get all of this, and negative because of the way I do the derivatives. That is, I want, So the way I do the derivatives, I want it to be the negative of that. All right, so all of this then, I can factor out e to the at on the left, e to the at transpose on the left, e to the at on the right, and I get this expression. So by differentiating this with respect to time, I get these 2 terms, but I can then isolate things this way. So P1 satisfies this equation. So I get minus Q coming out. So actually I'm getting minus Q coming out of this, and that's part of what's going on. But So I get this expression, and this is P. Okay, this is P. It's the Q. And so the reason why we have a unique solution is because we have a unique Q. So this shows that P1 must be equal to P. So I assumed that there was another solution to this equation, and what I've gone through and shown is that that solution is equal to the original solution. Okay, and so this equation for a stable system, this equation is unique, has a unique solution. All right, now I'm going to talk about the proof of Lyapunov's indirect method. So Lyapunov's indirect method says I start with a nonlinear system, and I have this linearization AX, where f of x can be written in terms of x this way. F of x is equal to ax plus h of x, and so h of x is a function that satisfies this relationship. The limit as the norm of x goes to 0 of h of x over x is equal to 0. Okay, so that's the definition of, this is a defining property of h of x. Right, so that's what we have. All right, so since A is Hurwitz, then there's a P positive definite and Q positive definite solution to this Lyapunov equation. What I'm going to go through and show is that this Lyapunov equation actually gives us information about a Lyapunov function for the nonlinear system. So this Lyapunov solution can actually be applied to the nonlinear system as well. So this is a Lyapunov equation for the linear version, and I can show that it actually gives us a Lyapunov function for the nonlinear system. So, which kind of makes sense because you're looking at the system at a particular point, right, in the linearization, and so if it works for the linear version, it should also work for the nonlinear version, at least in some neighborhood of the equilibrium. All right, by the definition of h, remember we had h that involved that limit as h of x over x goes to 0. We know for any epsilon greater than 0, generally small, we can show, remember since that limit went to 0, that h of x is in norm is less than epsilon times x. So as long as the norm of x is small. Okay, so that's what this is saying. For all x less than some value r. I can pick an r so that h is arbitrarily small compared to x. So since the limit of h of x over x in norm goes to 0, I can always find h of x arbitrarily small that way because of that limit. So for epsilon small enough, for example, epsilon less than this quantity, like, obviously there's a little that's gone on to find this quantity, but we've actually seen this kind of quantity before when we were looking at the exponential stability bounding for the continuous time system. So I'm going to assume now this inequality is satisfied. I'm going to pick an epsilon that's this small. Since for any epsilon greater than 0 there is this, so I'm going to choose epsilon small. I'm going to choose epsilon less than this quantity. So this inequality can be shown to be written as this inequality. Okay, it can be shown to be that inequality. So lambda min of q times the norm of x squared is greater than 2 times the norm of x, norm of h, and lambda max. All right, so we have that situation. I'm going to define this scalar quantity m to be the difference between those two numbers. Okay, so here I have that this number is strictly greater than this number. And so I'm going to let m be this quantity, and since this number is strictly greater than this number, then m is strictly positive. Okay, having done that now, here is my candidate Lyapunov function. I take the derivative along the system trajectory, f of x, so x dot p x plus x transpose p x dot. X dot is given by, so this is f of x transpose. Here's f of x. Okay, so I can group some terms together. So notice I have I can group these two terms together, x transpose A transpose P plus BA times x. I can get that. And then the other terms I can group together. And I can show that they will be equal to this. I'll get 2 times those. This quantity can always be shown to be less than or equal to this quantity. And this quantity here can be shown to be less than or equal to this quantity, lambda max, right? So the lambda max of P, the norm of H, the norm of X, okay? So this is like an inner product between X, a P inner product between X and H, and I can show using the Cauchy inequality this property. All right, so I have that. This quantity is the negative of this. It's minus m. So this shows that x dot is negative. That shows us that it's negative definite. Okay, this is negative definite. So what we've shown then is for some neighborhood of the origin. So this is basically a description of a neighborhood of the origin. Okay, and so this epsilon is basically shows that within this size neighborhood, we're stable. Now, it's possible I could find actually a larger neighborhood that could make it stable, but this one will allow it to be stable. So I have an example of this in the practice problems that you can look at and see how that looks like. So stay tuned for the practice problem.